Welcome to Wales Tech Week 2021. Thank you to our partners. Enjoy the session.
Hello everyone, I'm Hannah Fulliger, Events Coordinator at CSA Catapult. We're pleased to host and welcome you to Opportunities in Wales for DER as part of Driving the Electric Revolution at Wales Tech Week 2021. This session follows the international vision for DER and delivering PEMD excellence, which will be available to view soon if you weren't able to join earlier today. We'll be hearing presentations from Dr. Mike Jennings, Associate Professor at Swansea University, and Rob Harper, RF and Power Manager at the Compound Semiconductors Centre. Please post any questions for Mike and Rob in the comments throughout the session. There'll be a Q&A towards the end. If you can please post who your question is for, that would be really helpful, thank you. And if your question is for both speakers, that's absolutely fine too. I'll now hand over to Mike to begin. Thanks, Mike.
Thank you very much, Hannah, for the nice introduction. Can I just confirm you can see the slides? Yeah, hopefully you can see the slides, guys. I'll take that as a yes, and I'll crack on. So what I plan to do today is to just give you a little bit of an introduction as to some of the projects that Swansea and the wider cluster are working on in terms of DER, or Driving the Electric Revolution, which are really aimed to promote and establish really a power electronics, machines and drives, that's PEMD, a PEMD supply chain. So I'll speak about a project which is ongoing called Socrates, which is about a trench etch for a power transistor process. I'll discuss the Driving the Electric Revolution Industrial Centre that's just been funded recently in March. And in terms of Swansea, what we are doing on DER is we're establishing a centre for integrative semiconductor materials, and I'll just discuss a little bit about what that is. Okay, so Socrates, okay, it's a lovely name, and it's really about introducing to the UK, Wales and the UK, a specific process for creating silicon carbide transistors, all right, power transistors. Why are these important for PEMD? Well, basically, power electronics, machines and drives depend on these power transistors to deliver electrical energy to the motor. That's obviously an automotive example, all right? But, you know, if you imagine a wind turbine, for instance, you need to condition that electrical energy to be able to connect that generated energy to the grid, all right? And that, again, requires power electronics, and specifically requires this underpinning power transistor technology. It's really estimated, right, that within the next 10 years, 85% of all energy we use in the household, in the car, in the train, whatever type of energy we'll use, will flow through some sort of power electronic transistor, right? And so therefore, this is really a key enabling underpinning technology in order for us to be able to meet our climate change targets, etc. So onto the specific project then. So we have a number of cluster partners associated with this, SPTS. They are really a semiconductor manufacturing tool seller. So Newport Wafer Fab is a chip manufacturer. So they manufacture these types of power transistors, okay? And you can see a photograph of a power transistor over there. That's about 4 millimeters by 4 millimeters, right? So it's quite a small device. And it's about 350 microns or 0.35 millimeters thick. all right? So quite thin. And currently this is all based on silicon technology. Traditionally, it's been based on silicon technology. We are looking, for a more energy efficient alternative, which is why we're looking at this material, silicon carbide, all right? So Newport Wafer Fab manufacture these types of chips, okay, in Newport there, and SPTS provide them with the tools to do that, okay? So they're a tool manufacturer for the types of processing required to manufacture that chip. We've got CS Connected, Center for Integrative Semiconductor Materials at Swansea University, and I'll mention that a little bit later. But basically, the idea of the project is to introduce this really important process, okay, into the supply chain without the ability to be able to etch. So etch is creating like a little trench, right, in the semiconductor. Without that ability, we won't be able to manufacture these state-of-the-art devices, okay? So I should say that silicon carbide is already commercial. It's already commercial, but it doesn't exist in the UK, all right? And we need to make sure for our electric cars, for our energy generation, our renewable energy applications, for our trains, we need to make sure that we've got this technology. Otherwise, we're totally reliant upon it coming in from abroad. And, with Brexit and everything else, we're going to pay more, we're going to pay top dollar for it, right? So we need that capability here in the UK, in Wales. So the trench etch will enable silicon carbide trench MOSFET. Okay, so yeah, so this process, what that's saying is that this process is fundamental to creating these types of chips, right? It's fundamental. And specifically what the trench actually does, right, is a cross-section. So if I was to take a cross-section, you can see a cross-sectional image here. It basically allows you to put devices on a wafer, on a silicon carbide substrate. It allows you to put more devices per substrate on the wafer for a given area, okay, for a given area. So that it means that you can get more buck for your material, right? So it's important that and that translates into competitiveness. We've got to be able to compete with our customers. Newport Wafer Fab need to be able to compete. So this is really an important technology. And in terms of the main objectives, right? In the future, we are going to hope the DER funding has allowed us to buy a lot of equipment to do this, right? To do this trench process. But in the future, we want to scale that technology up so that Newport Wafer Fab can produce, in the region of 1,500, 2,000 wafers per week based on this process, right? Based on, this is one process in a string of processes, but based on this technology. Okay, so yeah, as I mentioned, high volume manufacturing is key. And you can see that this project was funded by Innovate UK and the Driving the Electric Revolution fund, right? So this is a nice picture, okay? This is a picture of Newport Wafer Fab. And as I kind of alluded to just a second ago, okay, phase one is a bunch of funding, about £5 million worth of funding that we have acquired from the Driving the Electric Revolution call, which was administered by Innovate UK. It's to create, it's money for about 5 or 6 important tools so that we can demonstrate this trench etching and power MOSFET process in the context of a manufacturing facility, which Newport Wafer Fab is. So that's phase one, right? And we're looking to do that in Fab 10. So if you look at that image, okay, most of Newport's, that's about a 3,000 meters squared clean room, okay, on the right there. A clean room is what the manufacturing floor, basically, for in the context of a chip. So this is Fab 11. This is where most of the manufacturing goes on, and Fab 10 is kind of some of the manufacturing, the later stages of the chip process go on in Fab 10. But actually, there's a lot of R&D activity scheduled to take place in Fab 10. So this kind of prototype manufacturing line will go into Fab 10. All right. On that line, we will prototype vertical, what we call planar. Planar are the more traditional types of power MOSFETs, right? And the new trench, which we want to bring to this sector. Okay, so we'll prototype these two different types of design architects. MOSFET stands for metal oxide semiconductor field effect transistor. Don't worry about that. It's a bit of a mouthful. It's just a transistor. It's an electronic component, right, which is really important for conditioning the electrical energy to drive your car, to heat your, to put your kettle on, to heat your, to convert the wind energy to the grid. This kind of application. In phase 2, right? Phase 2 is already underway. In fact, we plan to take this prototype and, as kind of alluded to earlier, scale it up to about 2,000 wafers per week, so that we can make some money out of it, right? So that Newport Wafer Fab, well, principally we bring that technology to Wales, and all of that profit, all of that money will contribute to job creation. Okay, it'll contribute to perhaps getting other electronics companies to start up within the region. And, it could really help us in terms of PEMD here in Wales. So this is really the last slide from myself, right? So this is the Centre for Integrative Semiconductor Materials in Swansea University. Now, I've spoken to you a lot, right, about power electronics, because Socrates, driving the electric revolution, is all around power electronics, really. Okay, it's in the field of power electronics, right? But SISM is dedicated to all of these other areas as well. So we've got photonics and data communications, okay, opto and energy systems, and biosensors for the medical kind of sector, right? So this is really the Centre for Integrative Manufacturing, Integrative Semiconductor Materials is a £90 million project, okay? £30 million from the government, from Research England, all right? And matched 2/3, so the other £60 million comes from our industrial partners, okay? Newport Wafer Fab, IQE, SPTS, and CS Connected. You can see the logos down here, right? So, and it's not really a traditional kind of university facility, in that the main goal of it is to support industry, to really demonstrate and get industrial contracts in, so that we can process semiconductors for industrial partners, principally within the cluster, but hopefully in the future, in a more global context as well, right? And it's a manufacturing grade R&I wafer fab, right, that supports regional industry, as I just mentioned. But crucially, we should be able to use this foundry. It's going to be like a foundry service, okay? Not going to be as big as Newport Wafer Fab, certainly not competing with Newport Wafer Fab or anything like that. But hopefully we can support those guys to help them with their kind of manufacturing processes, and we can chip in and help them with some of the process, take some of their wafers and run a back-end process or a trench etch or something like that, right? That's about it from me for today. So thank you very much for that, guys. I hope that was interesting for you. I know I took a lot of Rob's time last time, so I was deliberately made it shorter. So hopefully that's okay.
Thank you very much, Mike. That was a great presentation, and I'm pleased to invite Rob Harper to share his screen and begin his presentation with plenty of time, it seems, this time. Thank you.
So good afternoon, everyone. My name is Rob Harper. I work for the Compound Semiconductor Centre. I do a lot of work with Mike Jennings at Swansea University, and Mike's presented already on silicon carbide. I'm going to tell you about the capabilities we have regionally within gallium nitride, and the two materials are pretty complementary, and it's good to be following on from Mike, because he's already explained what the compelling reasons for moving to wide bandgap materials is, in terms of improved conversion efficiencies, faster switching speeds, higher breakdown voltages, etc. So If you could move on to the next slide, please, Hannah. So I think Mike and maybe a lot of you are familiar with some of the companies that are within the regional cluster. So we have a cluster called CS Connected within South Wales, and that's made up of both industrial and academic partners. And probably what's less well known is the fact that each of these organisations has some very advanced capabilities in gallium nitride. So Mike's already told you about Newport Wafer Fab down on the far right of the picture there. So they are, the UK's largest semiconductor chip foundry. So they have historically had some gallium nitride process capability when they were part of International Rectifier. And we're working with Newport to develop gallium nitride foundry processes through that facility. If you look at Microsemi, if we continue around in an anti-clockwise fashion, then they are experts in wide bandgap packaging. So actually packaging the chips that are coming out of Newport Wafer Fab and putting them into packages so they can be assembled into modules and integrated into system level products. Mike's already mentioned Socrates from a silicon carbide perspective and the work that he's doing with SPTS on trench etching. I'm doing a parallel activity with SPTS in gallium nitride trench etching. They manufacture the tools that Newport Wafer Fab used to manufacture the chips, so it's extremely useful to have companies like this within the cluster. And then if we move around to the catapult on the 12 o'clock position there, then we're working with the team at the catapult to develop the process design kits that allow designers to design on the types of processes that will be ultimately running through Newport Wafer Fab. We're working on RF devices at the moment, but there's an ambition to do that on power devices too and develop power PDKs. A few words about the academic partners. So top left we have the new fab that's being built in Cardiff on the Maindy site. So this is a 1,400 square metre clean room. And part of the expertise there really is focused on gallium nitride RF. So these are, advanced processes for high performance RF devices, which are used in defense, space. If you look at the 5G infrastructure now as well, they're very much needed for that type of application too. And I'm working with Mike and the team down at Swansea on GaN power development. So we have some active projects with Swansea University. Mike has already mentioned the new fab that's being built there, the Centre for Integrative Semiconductor Materials. And, we're doing a lot of work with Swansea and the cluster partners to develop processes and, extend the capability in silicon carbide and gallium nitride wide bandgap materials. Last but not least, there's IQE. I couldn't leave them out. I actually worked there for 15 years of my life. And they have a very advanced gallium nitride epi manufacturing capability. So the advanced substrates that these devices are built on are manufactured in Cardiff and come out of the facility at IQE. And recently, you probably already heard that IQE have expanded the operation at the new site on the fringes of Newport, and now operate the largest epi wafer foundry in globally. I mean, it's a huge facility, 360,000 square feet. So we have ambitions to extend the gallium nitride capacity at that building. So there's a huge amount of expertise regionally. And what I would say about that expertise, it's all very complementary. We're an end-to-end supply chain from materials right through to packaged devices regionally. And that's pretty unique globally. Not many people have that. It's a real strength of the region. So Hannah, could you move on, please? Next slide. Okay, so a little more about the projects that we're working on. So lateral HEMT, so high electron mobility transistors, have been around for quite some time. We're working really at the leading edge of what's available. So we're talking about a 650 volt device being manufactured on 200 millimeter gallium nitride, which again is then being grown on 200 millimeter silicon wafers. So this project's really about the gallium nitride epi material development and also setting up the key processes that we need at Newport Wafer Fab to develop a full 650 200 millimeter 650 volt, 200 millimeter GaN silicon process at Newport. And the other expertise that we're kind of looping into that is the expertise at the Centre for Thermography and Device Reliability at Bristol University. So Michael Luren, Martin Kubal and the group there have a very strong, they've been working on gallium nitride device reliability for some years. And it's always been an issue. I mean, the reason that gallium nitride hasn't moved into the marketplace as quickly as silicon carbide has is probably because of a problem called dynamic on resistance, where when you start operating the device, the device characteristics change unacceptably as the device is switched. So we're looking to resolve that issue, and dynamic R-on is the dynamic R-on performance improvement is the core focus of this project. So the project is being funded through Driving the Electric Revolution. So thank you all for the funding, and it's really all about establishing the first steps of providing material and the core processes to build a fuller UK capability in leading edge gallium nitride power technologies. So the one thing the way that this is working is that we're growing the materials at IQE, so these are 200 millimeter gallium silicon wafers, and we're then processing those from Newport Wafer Fab and assessing the electrical performance of those wafers with respect to the dynamic R-on characteristics. And this is a short loop process. The project name slogan, the first three letters stand for short loop optimization of GaN. And we are making some really, really kind of interesting finds by having this, the short loop process, which allows us then to make iterative improvements to the epi design. And we've actually modified the epi structure quite significantly through this project. And, we've certainly ended up with a more robust epi product as a result of that. So the tool down on the far right that you can see there, that's the gallium nitride epi reactor. This is a MOCVD, or a metal organic chemical vapor deposition system that we use to grow the gallium nitride wafers. It's state of the art. It's capable of running 5 8-inch wafers simultaneously. It's probably the tool of choice internationally, for this application in terms of cost of ownership and the advanced process control it offers. So all in all, this short loop process, and this, it's only been a short project really. It's a 12-month project that has delivered a solid platform now to accelerate the fuller 200 millimeter 650 volt GaN HEMT at Newport Wafer Fab, and it's proved very useful for that purpose. So if we could move on to the next slide, please. So as I mentioned, having all this regional capability allows us to almost spin pass wafers from one partner to another. And if it hadn't been for COVID, we'd have all been working in each other's facilities alongside each other, but that wasn't possible last year, as you can imagine. But we grew a lot of wafers. We grew probably about 200 wafers during this project time. and those wafers went into Newport, and we worked with the engineering team at Newport and Bristol to optimize the processes we needed to, get the wafers advanced enough so we could do the full electrical evaluation of the wafers. So, part of this was the design of an electrical test plan for characterizing the gallium nitride epi, and we've basically worked well with Bristol, and we've now provided an electrical equivalent circuit to allow us to optimize the epi design, and that's also allowed us to optimize the processes at Newport too. It's not just been about the epi; it's also been about optimization of the key processes that Newport are using to develop the full flow process for the gallium nitride HEMT. And the other thing that will come out of this really is the definition of a roadmap. So we're already clear on where we're going next and how we're going to scale this up. And there have been follow-on projects. One called Gandalf, which has basically established a clear route to volume scale up in the UK for gallium nitride HEMT devices. And the other great thing about working with Newport and working with IQE is that all the processes that we've set up have been demonstrated on industry proven tool platforms. So we're using the tools at Newport and the tools at IQE that they're industry ready. We're not doing this in a lab, we're doing this in real manufacturing environments, which again is the way to go for this. So if you could move on to the next slide, please. So that may look a little small to you, but the cross section on the top left of the slide there shows the structure of what we're doing here. So we're basically starting with an 8-inch silicon wafer. So these are 1-1-1 orientation, which facilitates the growth of gallium nitride. And then we'll grow in something called an SRL, or stress relief layer. And this layer allows us to adjust the lattice constant between silicon and gallium nitride by transitioning from one lattice constant to another. So gallium nitride has a different, the way that the atoms are spaced within the crystal structure means that they don't necessarily align with a silicon crystal that we're growing on. So we need to get this this engineered layer that's called the stress relief layer into as a first layer. There's a doped gallium nitride layer shown in green there. This is carbon doped gallium nitride, and on top of that we grow the channel layer, which is pure and undoped gallium nitride. On top of that, then we grow an algan layer, which because we're introducing aluminium into the layer, kind of induces strain into the surface channel, and you get something called an inverted piezoelectric effect, which basically gives you a very high carrier concentration across the surface of the channel and provides you with high mobility. So this gives you ultra fast switching speeds and lots of other desired characteristics. And importantly, by making some changes iteratively through this project, we've been able to greatly improve the dynamic RON performance. So you see on the image on the bottom right there that we've been able to modify the epi structure significantly through the length of this project, and we have greatly improved the reliability and the dynamic RON performance. So that's been a really successful outcome, and we're basically finishing this project at the end of June. So it's been challenging. We've been working through COVID restrictions, obviously, but Bristol University and Newport Wafer Fab themselves have managed to stay open and operational through most of that time. So that's been It's been good. So on to the next slide, please, Hannah. Right, so I'm going to talk about something which is slightly lower in terms of technology readiness level. I'm not sure whether you're all familiar with technology readiness level. I mean, obviously some things are closer to market and closer to manufacturing than others. The whole point of having a developmental roadmap is, you need to start working on some of the more advanced structures early on. So we have a steady roadmap of moving from maybe 600 volt devices to 1200 volt devices. Mike's already mentioned the benefits of vertical silicon carbide transistors. A lot of those same arguments apply to vertical gallium nitride transistors as well. So we are working with Swansea University with SPTS again on the process development. Newport Wafer Fab, the Catapult, working on the packaging and testing solutions for us. And we're basically developing a new type of transistor here, which is a vertical gallium nitride transistor. Not easy. It's in silicon, you can actually dope the different layers of silicon using a technique called ion implantation to give you an NPN sort of structure, but that's not possible with gallium nitride. If you try and implant it, all you do is you destroy the crystal structure of the material, and you can't kind of recover it by annealing it. So we've had to control the doping of the structure by in situ doping the structure epitaxially. So we've actually had to grow differently doped gallium nitride layers on the surface of this material. And that's been extremely challenging. So we're using silicon for the N-type dopant in this case. We're using magnesium for P-type dopant, but P-type dopant in gallium nitride is extremely challenging. The magnesium likes to diffuse, and it doesn't like to activate that well, so you can put tons of the stuff in, but the actual electrical concentration of the material, the amount of magnesium that's active in the device remains low. So we've bumped into challenges at every step of the way. So that said, we basically overcome a lot of the challenges, and we recently announced our first working devices, which is a great achievement at Swansea University, and we are now kind of halfway through the project, and we now have the other 12 to 18 months of the project remaining to optimize the device. So these devices are probably 3 to 5 years away from market. But it's important that we research them and develop them regionally so that we have a capability within the cluster to be able to manufacture these. The reason that we kind of want to do this is because HEMTs are pretty much limited to about 650 volts at the moment, and vertical devices will allow us to exceed that. We can move into the 1200 volt device operation in the future with this. Mike's mentioned that we're working with SPTS on silicon carbide trench, but if you look at the bottom right of the slide there, you can actually see some of the work that's been done at SPTS in developing the vertical trench etch for this type of device. So we've etched down through the magnesium doped GaN onto the N-GaN, and we will have a vertical channel along the vertical edge that you can see there. And again, we've basically done a lot of work with SPTS to optimize the profile. The profile there is pretty much optimized. It has a nice rounded corner at the bottom, which is highly desirable because it removes a high field point from that corner. If you micro trench into that corner, you can end up with premature breakdown of the device. So, you know, a lot of good work's been done within this project to optimize the trench profiles, to optimize the epi doping, you know, to give us the desired electrostatic control of the transistor. And it's been pretty successful. And again, you know, I mean, we've been thwarted by COVID throughout this. Swansea University had to close their labs, but we're now back on track, and we see this vertical platform as the ideal way of scaling the voltage without increasing the chip area. So ultimately, this will become more cost-effective than lateral gallium nitride heads. So if we could move on to the next slide. So in summary, you know, I think within the cluster, we are developing some really great gallium nitride process and fab capability and materials capability. And the other thing that I've predominantly focused on power here, but there's also been a parallel activity on gallium nitride RF development. And these two things go very much hand in hand, you know, I mean, to have the same capabilities that you need for GaN power pretty much fit for GaN RF as well. And RF is very much, you know, it's a strategic issue, you know. I mean, we've seen what happened with Chinese supply and us not having the correct UK capabilities to install our own 5G infrastructure. So again, this kind of moves towards that sort of capability regionally. I'd like to thank DER and the APC2 for funding to do this type of work. I think you know, both projects have been extremely useful in developing the capability and you know, putting together wider ambitions to kind of well, put in place the pieces that we need to industrialize this in the future. So again, I'd just like to say that, you know, the region, the South Wales region, does have a unique joined up capability. Not everywhere in the world has that. It's typically what you see within the GaN businesses, that, you know, people will have wafers, epi wafers supplied from the US, maybe run them in Japan and have them packaged in Malaysia. And to be able to do that all in a single region, you know, and have a turnkey solution is a really strong USP. So the one thing I'd like to say, as well as all the work that's being conducted so far, is that we're just embarking on some additional gallium nitride technology development through Strength in Places funding. So a lot of the CS Connected partners are involved in that. And as well as developing the technology roadmaps, we're also developing supply chains, which is extremely important. So there's an underlying supply chain development in all the projects I've just mentioned to you too. So I think that's just about me done. So thank you very much for your time. Happy to take questions, and if you need to contact me after this, then my contact details are there in blue. Okay, so thanks again.
Thank you, Rob, and thank you, Mike. If I can just invite you both to come back on camera, and we can open the floor to questions. I haven't seen any come through on the comments section just yet. So I'd like to ask you, is there anything further to your presentations that you'd like to add, or anything you'd like to ask each other?
You first, Mike.
We speak most days, don't we, Rob? So
we do, yeah. Most days. But, you know, I mean, one thing, I mean, Mike's not just looking after silicon carbide, and I'm not just looking after gallium nitride. We're involved in both materials. And the other material that Mike's really interested in is gallium oxide. So there is a roadmap to move us from where we are today into where we need to be in the future. So in terms of
absolutely. In fact, Swansea, we just got another grant from EPSRC, Professor Stuart Irvine, which is the Engineering and Physical Research Council, EPSRC, right? Physical Sciences Research Council, and that's to grow gallium oxide, which is like the new material. We're probably looking, it's a very low TRL. Rob spoke about TRL levels. This is quite a low TRL level, but in the future, it's really exciting material, in my opinion, because as opposed to silicon carbide and gallium nitride, right? Gallium oxide can be grown from traditional, the same way you create silicon wafers, which is a lot cheaper, a lot easier than it is using seed sublimation that you do for silicon carbide and CVD, I guess, Rob, right, for gallium nitride. So it offers the prospect of being much cheaper and potentially more efficient as well. There are problems, with the thermal management of gallium oxide. That'll be the issue, but it's exciting, yeah. And in power electronics now, because I focus myself on power. Rob's mentioned that gallium nitride in particular is excellent for RF, for high frequency fast switching applications as well. But in power electronics, the trend now is to integrate, is to shrink everything, right? To make it lighter, smaller, more efficient. So what people are doing is trying to put the power electronics literally onto the machine casing, right? Onto the really close to the machine. So you make the powertrain much more compact. Gallium oxide lends itself well to that because you can sputter it onto stuff, and when you sputter it, you can make it an insulator, a semiconductor, or a metal. It'll conduct as well. So it's quite an exciting material, I think, for the future.
Yeah,
for sure.
And it's important to work on all these materials and bring them through the TRLs, because typically Innovate UK wouldn't fund something as low TRL as vertical gallium nitride devices. But with the project that we're doing at Swansea, and that was funded through the Office for Low Emission Vehicles, we can get that to TRL 5, 6, 7, to the stage where it could be funded by standard Innovate projects.
Yeah.
So, and again, we need that steady stream we need that kind of materials roadmap as well as the device roadmap. So we need the materials as well as the new device architectures to make sure that we can compete globally. And if we look, Mike and myself have got one eye on what's happening in the rest of the world too. So if you look what the other research groups are doing with in relation to wide bandgap materials, then we've got to watch and brief.
Yeah, in fact, just before this meeting, I came off a European project that we're closing up, Rob, on cubic silicon carbide, which is another form of silicon carbide, and there's a load of interest in this now. There's a load of interest, and in the wider context, semiconductors. I don't know if you read the news just yesterday. There was something about Ford having to stop. I know Ford in Wales is a terrible story, but Ford globally about to stop manufacturing cars because they can't get enough semiconductors, right? So, Rob and myself, we speak about semiconductors in the context of power electronics and RF, right, and high frequency communication amplifier systems, but actually it underpins the semiconductor materials that we're talking about underpin loads of different application areas, from artificial intelligence, Internet of Things, right, sensors. Your cars even now are full of semiconductors, and they're not fully electric yet, right? When they're fully electric, which they will be before long, that this technology is going to really underpin everything in your car, pretty much. I don't know if you agree with that, Rob. I mean, the battery's important, but the battery's important as well. But semiconductors are that underpinning technology, really.
Yeah, and I mean, there's definitely going to be a transition from silicon to wide bandgap materials as well. I mean, we see that happening right now. If you look at Mike's the material Mike talked about, silicon carbide, is already in the Tesla Model 3. It's being qualified on, I think, like 10 or 15 different models by Hyundai. So the Infineon process is being evaluated for that. So it's about to mushroom. And at the moment, I mean, one thing I would say is that the UK currently doesn't have any capability in silicon carbide, either materials or processes. And so we're looking to address that. But the one thing I would say about gallium nitride is here and this now. I mean, all our cluster partners have some really advanced, great capability in GaN. And they're all working on different parts of the supply chain. It's all highly complementary. And if we can't do something between us with what we have in place, we're missing a trick.
Definitely. It's so important that we're in this game. It's so important for us to meet our energy targets, for us to be able to develop our own Internet of Things platforms, artificial intelligence platforms. You have to have. It's all built on semiconductors, right? You have to have a national capability for sure.
Yeah.
So this is what we're trying to establish, really, Rob, isn't it? Moving forward.
Having said what I just said, Mike, I'd also say that we are working together. I mean, there's been a lot of really encouraging development of processes and capabilities over the last 2 to 3 years, maybe a bit longer. Yeah,
absolutely. Yeah.
It's great that it's really good that everyone's communicating really well. I mean, we can pick up the phone to SPTS or Newport Wafer Fab or the Catapults. We're all kind of talking, not so much to you, Hannah, but we're talking to Tudor, we're talking to Ingo, we're talking to Alistair. There's really strong communication that's really facilitated, or would have been had we not had COVID, but it would have been facilitated by the fact that we're all each other's neighbours almost.
Yeah. Exactly. And the other thing, the other important point that you raised earlier, I guess, is skills, right? So, if we're going to grow, I mean, SPTS are expanding their manufacturing capability massively, and most likely Newport Wafer Fab. I'm not sure about IQE, Rob, but I'm sure they plan to, some of those, certainly Newport Wafer Fab plan to grow, right? But we'll have a shortage of people then, and one of the things that we've just done in Swansea to try to address that is Professor Owen Guy, who's head of chemistry here, and myself, we've developed a new MSc in semiconductor technology and applications, which covers all of the things we discussed, from power, RF, right the way through to sensors. Not so much on the RF side, because that's well covered by Cardiff University, actually. But and it's so important that our industrial partners can send and upskill, right, some of their staff. In terms of, so you might have people coming in from the automotive industry, say, to Newport Wafer Fab, working on the line, right? And maybe it's the first time they've seen a semiconductor, do you know what I mean? So it's important that we have the infrastructure in place to be able to upskill those guys and give them some theory around, the basic theory around what they're doing in the semiconductor industry. And there's obviously existing industrialists is targeted at, but also, bringing new people into the region. That's got to be another important aspect of it as well. So, yeah, this is all happening actually.
Yeah, it's good to see that.
And when you say about bringing new people into the region, that's all the more important, because that will fuel collaboration further. I'd like to thank you both. You've made my job in hosting the Q&A very easy there. Thank you. I'm really interested to hear about your new MSc at Swansea, and to kind of maybe say, we've only got a couple of minutes left, so if you could say anything further on the future applications, that the future materials that you're talking about are going to help bring to market and bring to our society, and the benefits there. Can you say any more about that?
Sure, yeah. Certainly, if you look at the big market at the moment, it's electric vehicles. So not just the vehicles themselves, but the charging infrastructure. So they go hand in hand. And I think Mike and myself both agree that these vehicles will go full battery. They'll in a few years' time, there'll be no such thing as a plug-in hybrid. That, you know, things will just be all battery. And the reason for that is, you know, if you have a plug-in hybrid, you have the worst of both worlds. You're either carrying around a really heavy internal combustion engine if you're running on the battery, or vice versa if you're running on the IC engine. So that's the big marketplace. You know, there are some really lucrative markets in RF, in 5G and defense and space. And to be able to offer high volume, wide bandgap processes for power and have this complementary RF capability, you know, alongside that, it allows us to run both businesses profitably through a fab. Whereas it's always difficult to justify investing huge amount of money into a sovereign RF capability. So yeah, so there are some small niche applications, but Mike outlined you know, just about everything that involves power switching, whether it's power electronics, motors and drives, automotive, aviation. If you look at DER, you know, it's so cross-sectoral. I think there was 7 different sectors within the EMD that we identified, including rail traction, marine, off-road vehicles. So they're all individually huge markets, but the one that kind of dwarfs them all really is the automotive at this stage.
Well, I totally agree, Rob. I totally agree. And the thing is, you know, I mean, Boris has said, hasn't he, that he doesn't want any petrol engines by 2030. We've got a lot of work to do if he wants to do that, right? But for, you know, to create the infrastructure for it, not just, you know, the semiconductors, but obviously the grid infrastructure. But I agree. I mean, and I think the important takeaway is, you know, I agree with Rob. It's probably going to go towards, you know, battery only technology. But all of those technologies, where even hydrogen, they all need power electronics, right? They all need semiconductors. It doesn't matter if it's a hydrogen fuel cell, a plug-in hybrid, right? Straight hybrid, or an electric vehicle, or a pure electric battery electric vehicle. They all need these they're all going to need the semiconductor materials that we're talking about. You know,
and they need the wide bandgap too, Mike, just because of the efficiency improvements, right? Because it gives you better range. I mean, although they're more expensive over the lifetime of the vehicle, they pay back.
Yeah.
So,
And you know, that's right, Rob. And even in energy as well, the biggest market is by far automotive. But you know, if we're talking about wind energy is going to be, you know, that's. We're trying in the UK to produce the majority of the energy we use now, electrical energy, from wind. I mean, you know, when you consider that, you know, the number of power electronic converters that energy will travel through before it gets to your kettle is about 5 or 6, you know, each with a loss across them, you know, each with an efficiency associated with them. You know, it becomes really important then. Do you know what I mean? Because it's the difference between like 60-70% efficiency compared to 90%, 95% efficiency. So, you know, what it means is that what power electronics, if it's efficient, what it'll do for you is mean that you have to generate less energy to begin with. Do you see what I mean? You know, you deliver the energy you generate more efficiently. So if you're doing that, you don't need to generate so much, right? So you reduce your demand, essentially, demand capability. You reduce the amount of energy you need to produce, which can only be a good thing. Burning less coal, or less making less wind turbines. So that's what power electronics can do for you, is really make the system efficient. Yeah.
Thank you. I've scribbling notes because I've really enjoyed this discussion. It's been so interesting. Thank you. And I think that power electronics, what it will do is mean that you don't have to create as much energy in the first place, is quite a statement to end on. So I'm just mindful of time. So I'd like to say a big thank you to Mike and Rob for presenting, and as I say, for such a valuable discussion. We hope you enjoyed this session. I'd just like to, I think I'm still sharing my slides. If you do have any further questions for Mike and Rob, please get in touch with them, or you can email collaboration@csa.catapult.org.uk. If you do have any feedback on this session, Opportunities in Wales for DER, we'd love to know your thoughts, so you can email events@CSA Catapult. And do keep an eye on our social media and also our website for our latest news and future events. I've posted links to those channels on the comments. So I think that's everything. I'd like to say a big thank you to everyone and to all our speakers from our 3 sessions across Driving the Electric Revolution at Wales Tech Week. Thank you, everyone. Enjoy the rest of the week.
Thank you, Hannah. Bye-bye.
Thanks, Hannah. Yeah, thank you all.
Thank you for watching. Rewatch all of our sessions online. Thank you to our partners,